This video has been supported by Leadshine technology. Hey folks, I built my CNC machine in 2019, a year in which millions of homes all over the world are interconnected with a digital communications network that can transmit hundreds of megabits of data across continents with milliseconds of latency. Literally a ubiquitous technology. Meanwhile, in my CNC machine's control cabinet there is a high-tech, high-performance computer and similarly futuristic motor controllers a few centimeters away. Both chock full of silicon and enough processing power to coordinate a moon landing, yet to communicate a handful bits worth of positioning information. These devices rely on a primitive, interference-prone, one-directional communication method, the step direction interface, likely as old as stepper motors themselves, so from the 1920s maybe. And it wasn't even easy to install or anything. I needed an expensive FPGA card to generate the impulses and count the encoder feedback. And everything is connected with chaotic per signal per motor controller wiring. That's my fault though, I could have done this a lot neater. Still, atrocious things going on, while our high-performance, low-latency capable Ethernet port is sitting on the side, looking on in horror. Today I want to explore a remedy for this situation, something that is not yet very popular in amateur machines, like hobby CNC machines or 3D printers, but in my opinion, long overdue. I want my control computer and the servo drives to communicate digitally on a higher level, so that instead of having to be like step, they can go.
Good morning, how is everybody? Here's our shared clock for today. Please use your built-in homing and tell me your position. The operator wants to jog the machine manually. Let's reduce max torque in the event of a crash. Next up is a high-speed trochoidal milling operation for which we will use these specific PID values. For the finishing pass I need you to go to this position extra slowly and with the adaptive vibration filter enabled so that we leave the perfect surface finish.
Just some examples I made up, not sure if entirely realistic. But the high-level, bidirectional real-time communication via EtherCAT is going in this direction. The amazing hardware that we are going to demonstrate that with, as well as a big basket of cables and accessories, have been provided by Leadshine Technologies. Leadshine is a Shenzhen-based manufacturer and full technical service provider in the motion control field. Their products include cost-effective stepper motors and drivers, high-performance servos in all sizes and shapes, and soon programmable logic and motion controllers. The fact that their sales team understood immediately what I wanted to try, and suggested the perfect set of their L7 EC drives for the job, as well as one exciting box of indeterminate content, gave me a very good impression. If your project needs innovative motion control solutions for a reasonable price too, contact Leadshine or their North American office with the link in the video description below. What we have here are 6 motors that would most commonly be called AC servos on the street. However, a more precise terminology would be permanent magnet synchronous motors, because they have permanent neodymium magnets embedded in their rotors, and in normal operation the rotor simply follows the magnetic field that the stator coils generate synchronously. That on its own is not that unusual for precision motion control. The supporting technology for these, however, certainly is special. The smaller motors are not directly NEMA 17 compatible, because their flange is a bit larger. But I don't think there is any doubt about one thing: they are intolerably cute. They are not much larger or heavier than a 3D printer stepper motor, but according to their label, they can put out 0.64 Newton-meter torque, and that is going to be at any speed. A stepper won't even be able to match that while standing still. But torque is not what I want to use these smaller ones for. They are primarily for precise positioning. So I asked for their best encoder, and I think I got it. This small motor is supposed to have a 23-bit absolute encoder. I'm not sure if I'm going to be able to verify that at all, because if true, it divides a circle into over 8 million pieces. And as if that wasn't good enough, it's also got an IP65 rating, meaning that it's impervious to dust and low-pressure water jets from any direction. The big chonkers are equipped similarly, but I think there are a few mistakes on the label. They are supposed to have a 400-watt rating and a lot more torque. Torque is what I need those for primarily. They absolutely don't need any ultra encoder performance. But I'm afraid they equipped those same encoders anyway. Oh well, we'll see. No complaints here either way. The 100 and 400 watt motors come in different sizes, but their EL7 servo drives don't exist smaller than 400 watt. So we've got 6 identical 400 watt units, and I'm pretty sure that they are smaller than the ones that are currently driving my CNC machine. Still, they are full of features like adaptive auto-tuning, vibration suppression, automatic motor identification, and homing based on digital limit switch inputs. They have a built-in braking resistor and can be fed directly off of 220 mains AC. This way they need no additional hardware to work. I feel like I recognize that encoder input connector. Isn't that Firewire? It's pretty clever, to be honest, since Firewire cables use 2 screened, twisted differential pairs inside of another separate outer screen, perfect for an EMI polluted automation environment. And most importantly, we only have a small, tasteful selection of digital IOs, instead of a huge, intimidating high-density connector. One can tell these are meant to use EtherCAT for everything primarily. Let's take a test drive in the manufacturer's configuration software called Motion Studio. For that to work, you also need Microsoft Visual C++ 2008 Service Pack 1 Redistributable Package MFC Security Update. These low-profile power and encoder connectors by Sunshu seem to be IP67 rated thanks to a compression seal. The encoder cable has an inline cylindrical lithium battery that supposedly allows the encoder to remember its multi-turn position. I'm not entirely sure why anybody would want that, and what happens if the motor is moved while being powered off. I only know that this is a prestigious feature usually. The power connector below just needs mains input, earth, and the motor U, V, and W terminals. Careful, the wiring diagram in the manual shows a mains filter, but it's a bit easy to miss. If you do, like I did here, you'll quickly see that these guys, small and cute as they may be, are absolutely brutal in terms of conducted EMI. This one is straight up knocking my monitor unconscious. For now, I think I'll solve that with one of my many battery power stations. With that out of the way, we can take a look at the highlights in the control software. A setup wizard exists for the most basic settings. As advertised, the motor is recognized automatically and most settings are already filled out, like encoder type, maximum phase current or maximum RPM. What you can and should configure is the EtherCAT slave ID that identifies every participant in the EtherCAT network, and an internal encoder count divider that can be configured in such a way that all command and feedback numbers are given and expected in micrometer, and not some crooked fraction that depends on ball screw pitch or pulley ratio. You can also configure what the digital in and outputs do, but that's optional for now. Down here you can manipulate the position control loop parameters, if you dare. By default, this whole section is set to real-time auto-tuning. The position controller takes into account a lot of filter settings and puts out a velocity command, which is then handed over internally to another velocity control loop. That one also defaults to real-time auto-tuning, so I don't know. We'll have to give them a fair chance before refusing to work with such newfangled technology. And here's a full parameter list that you can import and export for backup and mass deployment purposes. So far, the settings are pretty uninviting and demanding of some knowledge in the operator. That's not very 2022, is it? Luckily, in the performance adjustment category, there are a few hand-holding assistants that can help with all the difficult decisions. First, there's a so-called inertia ratio variable that helps the control loops accommodate large masses that would much rather continue doing what they were doing before than listen to the erratic commands of a small servo. If such a mass is in motion, it will continue for a short moment even if the servo stops abruptly. The further away from its set point a servo gets pushed, the more forceful its opposing reaction will be, which will again set the mass in motion and create a growing, dangerous oscillation. This is not the kind of hand-holding I mentioned before, not recommended. Ow. It would be best to start the inertia identification assistant with conservative values. For example, 100 RPM, 1 second acceleration and 1000 inertia ratio. Then you simply define 2 motor positions between which test movements will be performed. And at the end, if it hasn't broken your wrist or knocked your teeth out with flying machine parts, it should come up with a suggestion for an optimal inertia ratio. In this case, roughly 7000, which is absurd of course, but then again, so is my machine. Ooh, that is scary. I'm not entirely sure what the inertia variable does, but since we are now hearing an additional lower frequency tone on top of the permanent singing of the motor, I'd say it just lowers some frequency components of the auto-tuned control loops. But yeah, it sure was effective. No more wrist-breaking, escalating vibrations. I'm sure in a more realistic scenario we wouldn't have to resort to such extreme inertia values that bog down the control loops all the way to audible levels. The next point, called gain adjustment, seems to be another representation of the position and speed control loop gains. We've met those before with a block diagram illustration, but here they are all in one place for convenient fine-tuning, and with parameters for all the filters that are applied somewhere along the way. It's quite easy to throw the previously automatically optimized settings out of balance and to create a risk of dangerous vibrations, so it's probably not a good idea to have anything attached to the shaft while the settings are far away from optimal. Uh-oh, it's whooshing. Can you guess why this 3D printed piece is already broken? Luckily, the servo drive notices this abnormal behavior and shuts down with an error state. That was fun, let's do it again. It's all fun and games with no or small masses attached to the shaft, but the peak power that these little guys can put out exceeds their 400 watt continuous rating by far, and that makes them quite scary. To prevent oscillations, we can try to enable the auto-tuning filter mode. In fact, I'm surprised that it wasn't enabled by default, because in the manual, Leadshine is quite clear about it. It's forbidden to non-professional users to go without this setting. Yeah, that makes perfect sense, because with this setting enabled, I can literally connect the worst thing imaginable to the shaft. A long, bendy arm with some added weight at the far end, designed specifically to promote vibrations, and is just completely chill with it. This is just using the automatic vibration suppression. If insufficient or if the frequency is too low, you can use the oscilloscope in Leadshine's Motion Studio software to determine the period and therefore the frequency of the vibration manually, and then pass the information on to one of two optional filters. That would remove such unwanted effects permanently. This apparatus is still a loaded gun, so I'd better stop playing with it before any innocent JBC stations get in the line of fire. Anyway, this was just preparation in Leadshine's configuration software connected via USB. What we are actually here for is the real-time EtherCAT communication. EtherCAT is a standardized bus system for automation technology. On the lowest physical layer, i.e. connectors and cables, and on the second data link layer, i.e. medium access control and frame synchronization, EtherCAT is actually identical to our good old Ethernet. That's why many ordinary network interface controllers in standard PCs can simply be configured to become EtherCAT interfaces. It makes for an especially cute arrangement with modern single-board computers like a Raspberry Pi or a Latte Panda Delta. But a friend has recently donated this incredible, passively cooled Core i5-based industrial control computer. It was made by Beckhoff Automation, the company where EtherCAT was developed. So of course it's optimized for it with two low-latency NICs. Single-board computers are nice and all, but this is clearly what we are destined to use today. While all imaginable network topologies like star, tree, bus, or combinations thereof are supported, most devices seem to come equipped with two RJ45 connectors, so that they can be connected in a line easily. Virtually, the participants in a network will form a loop. The master, which is usually a software running on the control computer, will produce EtherCAT frames. These are passed on from one slave to the next, while the data within is extracted or added to nearly on the fly. This way there are never any collisions on the medium. The time to reach each device and the round-trip times are deterministic, and that in turn allows for precise synchronization of a distributed clock, vital for multi-axis motion control. EtherCAT is already widespread and supported by many PLCs, motion controllers, servo drives, and even some trinamic motor controller ICs. But I'm sure there are many other high-performance automation solutions out there that can bombard you with buzzwords and cherry-picked advantages until you don't understand anything anymore. But here is my favorite thing of all. There is an open-source EtherCAT master available and functional on Linux right now that you can build and install on nearly any PC or single-board computer, including Raspberry Pis. There are several step-by-step instructions on the internet. I'll link one example below. The outcome is that you have a dedicated, exclusive EtherCAT port on your device, to which you can connect EtherCAT slaves with zero additional hardware. And then you can just type EtherCAT slaves -verbose to receive a list of all devices present. In this case, it's only a certain ELP EC400S. This first step was very easy. It only takes some dependencies from the package management and a few commands to compile and install the master. Pulling off this next trick took a bit more effort because we are pretty early adopters of LinuxCNC and EtherCAT, I imagine. But look, with one software layer in between, it is possible for LinuxCNC to control and read back positioning information from these servo drives. To do this, I installed the LinuxCNC uSpace dev package so that I can compile user space components. I think this is included by default nowadays if you use the latest ISO from the LinuxCNC website. The abstraction layer, the glue software that LinuxCNC needs to interact with the EtherCAT master that is now permanently running in the background, is also open source software available on GitHub. It's called LinuxCNC EtherCAT by Sidner and contributors, and it comes with a makefile that handles the compilation and installation for you. It even comes with all of these presets for likely the most common EtherCAT slaves, which are these stackable DIN-rail mount Beckhoff bus terminal slices. Next, we open Leadshine Motion Studio and give our first servo drive a memorable EtherCAT slave ID, like 0 for example. And we can keep this open and connected because we'll need it again immediately. For an absolutely minimal test setup, the LinuxCNC configuration consists of 3 files. First, a machine name.ini filled mostly with numeric variables. Fundamental stuff like joint velocity and acceleration belongs in here. Second, an XML file which describes your EtherCAT network. There is unfortunately little to no hand-holding available for this file at the moment, but examples of varying complexity are available in the LinuxCNC EtherCAT GitHub repo. It looks intimidating, but it's pretty descriptive on its own. You enter the slave ID that we've just configured, use a generic type for servo drives, or those pre-made ones for one of those Beckhoff bus terminals. The vendor and product IDs can be read with the EtherCAT slaves command line tool. And then there are the PDOs, the process data objects that actually matter to us. The PDOs contain the time-critical data that is updated often. We are sending some to the servo drive, like a control word, an operational mode, and a target position. And we expect to receive some back, like a status word, an actual operational mode, and the actual position. But modern servo drives are not only operated in position control mode. Maybe we are interested in commanding and reading torque or velocity values. Or we are a collaborative robot arm that is currently being taught a new movement. So we might want to disable the motor and only record position values over time. To remain flexible and open to such challenges, the PDO registers can all be reconfigured in the Leadshine Motion Studio software. Such flexibility can add a lot of complexity, so I'm going to leave mine as they are for the time being. Just note that there are tons of data sources and sinks available, and LinuxCNC can tap into everything if you wanted to. For non-real-time critical data, there are also SDOs, service data objects. Those are useful, for example, for an initial configuration of a device. But since our Leadshine kit has the automatic motor identification and online auto-tuning for all parameters that matter, I don't think we have to use any SDOs. But we have a third file that ties the LinuxCNC configuration together. The hell file, the hardware abstraction layer, where we actually load a kinematics component as defined in the ini file. This could be Core XY or Delta for 3D printers. But for this simple demonstration, trivial kinematics for a 3-axis Cartesian machine should suffice. We are also loading the LinuxCNC EtherCAT component that we've cloned from GitHub and compiled a moment ago. And we are initializing one instance of a certain CIA 402 component. This one doesn't initiate violent regime changes abroad for our economic benefits. It is simply an aid for interfacing with servo drives that comply with the CAN-in automation standard. It's a kind of state machine that wants to go through a few standard steps before becoming operational. We don't have to understand it all the way through, I think. Our Leadshine servo drives and most other reputable products comply with this standard, so it just works. The servo thread is kind of the main loop of LinuxCNC. It is repeated all the time, so we attach all the read, math and write functions to it. Here we are routing 3 input signals from our LinuxCNC trivial kinematics planner to named nets, only to forward them to the CIA 402 state machine. We are also giving it all the feedback that we receive from the EtherCAT component. And we also let it control what the EtherCAT component sends out to the hardware. Looks complicated, but in comparison to what we had to do previously, defining PID controllers in this file, etc., it's basically nothing. And for adding more axes, you simply have to copy the lower half a few times. And that really leaves us with this delicious setup where LinuxCNC can control a long string, I think up to 65,000 slaves or so, of very complicated hardware over an Ethernet cable in real time. If you want, you can imagine a Raspberry Pi instead of that Beckhoff PC, which would make the setup look even more slim. The Pi's NICs have been shown to work nicely, but the boards are pretty much unobtainium nowadays, aren't they? This is of course standing on the shoulders of giants who have created the suitable software and released it liberally under open source licenses. But from what I hear in proprietary solutions in the industry and in the Mach 3 or 4 software package, it's also possible and even easier to use. Not that I would know about such things. The EL7 servo drives have opto-isolator inputs with built-in resistors. That way one can very easily and safely connect limit and home switches without allocating additional GPIOs on the controller board or PC. But of course we can always read those inputs over EtherCAT. It has come to my attention that people are making a sport out of printing the fastest benchies that their over-engineered Voron printers technically allow. Now LinuxCNC supports CoreXY kinematics natively. I wonder if that has ever been done before. Should we give that a try? Are auto-tuning, vibration damping $1,000 servo kits in alignment with the rules of that sport? Or should we revive an old idea that I've teased a long time ago but never delivered? Leave a comment and let me know what you'd like me to do with these servos. But yeah, that was pretty much the main thing I wanted to demonstrate today. I only have 2 more things on the agenda. A quick superficial teardown, and I still haven't figured out if these really are 23-bit absolute encoders with this shaft angle resolution. While pondering my options of verifying that, maybe with the applied science laser diode power monitor trick. Or this Bloom production metrology 3D touch probe. A much easier option occurred to me. Why don't I simply have an oscilloscope count the encoder impulses of 1 full revolution? We don't need an exact revolution. The difference between a 20 and a 23-bit number is gigantic. It should be easy to tell. Well, there goes my IP60 rating. Alas, it's not so easy. In 2022, rotary encoders no longer produce something so simple as pulses per revolution, or God forbid phase-shifted sine and cosine waves. Instead, this heavily obfuscated part seems to respond only to RS-485 inquiries from the drive. But it looks and is labeled plausibly. It seems to be available through an elevator and escalator parts supplier. And at $300 in small quantities, it is likely the most expensive component per servo axis. No interfacing details are available, but it seems to be a drop-in replacement for a Tamagawa part. So if we were very serious about it, we could probably figure out how to talk to it. But no, I believe it. With the electronic gear ratio disabled in the software, it gives us exactly the correct integer representation for 1 revolution. Wow, check out the sensitivity to any kind of manipulation of the shaft. Hey, it's no nut November after all. Teardown ability of the servo drive gets an 8.5 out of 10 on the reps scale, for being effortless and not even needing any tools. But there is nothing terribly interesting to see inside. Absolutely no filtering of the input power on its way to a heat-sunk bridge rectifier, as we had anticipated earlier when the thing practically made my PC monitor unusable. The rectified voltage gets stored in 2 large Jiang high capacitors, not a brand known to me but with a 105C temperature rating, and a lot of DC voltage headroom. It should last for a very long time. From there, one of these all-in-one 3-phase power ICs takes over, shaping the rectified power into 3 AC signals at the discretion of this central controller IC, which has unfortunately been made unrecognizable. It would make no sense to take off the heatsink because we would just be greeted by the rear thermal pads of the power parts. So that's pretty much all. It's a neat, compact implementation, with plenty of optical isolation and conformal coating. It's a pity that we can't see the main controller, because it seems to be in charge of everything. All the communication with the outside world and the digital I/Os, the CIA 402 state machine, and a ton of digital signal processing in real time, based on all the motor drive filters and the long numbers coming back from the encoder. I'm seeing no external random access memory for that part, which might be a clue. I don't think there is a coprocessor hidden underneath the heatsink, because that would have to be on the isolated high voltage side, beyond that line on the board. And we have a little bodge for good luck. And that's all I got for today. Thanks to Leadshine for sending over such powerful hardware, and for giving me the freedom to advance one of my many pipe dreams with it. Thanks to the open source community for making next level technologies like EtherCAT usable freely by everyone. And most importantly, thanks to you for watching, making what I do here possible in the first place.